This is AI Papers, a deep dive, where we take one new research paper and actually read it, methods, results, and all. All right, let's get into it.
Researchers handed an AI more data about what its GPU code was doing wrong, and the code got worse. Worse than if they'd told it nothing at all. And this isn't a fluke they're hand-waving past. They ran the statistics.
Quick heads up before we start. This is an AI-made explainer, both voices included.
So here's the promise. By the end of this, you'll understand why, for one of the hardest crafts in computing, raw measurement data actively makes a language model dumber, and how a system built on that single, counterintuitive idea wrote a GPU kernel from scratch that beat the human experts who'd already hand-tuned the production version.
But let's sit on the weird part first, because it shouldn't be possible. Information isn't supposed to hurt you. Worst case, you ignore it. If I give the model the profiler readout and it doesn't help, fine. But how do you get to actively worse than silence?
That's the whole paper, really. The numbers. Feed the model the raw hardware counters, and you get an average speedup of about 1.8 times over the baseline. Give it no profiling data at all, just make this faster, and you get 3.3. The version with nothing nearly doubles the version with everything. And the gap is highly statistically significant. This is the result they're most confident in.
And why this matters beyond one paper. Writing fast GPU code is the bottleneck under all of modern AI. It takes scarce experts, and every new chip generation reopens the problem. So, can a model do it? And how should we wire it up? Is a question with real money behind it. The paper's the system called KernelPro out of Amazon, posted this week.
Let me set the table on what a GPU kernel even is, because everything hangs on it. A kernel is a small program that runs in massive parallel across the thousands of little arithmetic units on a graphics card, the code underneath every model's training and inference. Writing one that's correct is easy. Writing one that's fast is brutal, because the chip has a strict pecking order of memory. Registers are instant. Shared memory, on chip, is fast. The big off-chip pool, DRAM, is slow. A kernel that does the right math but keeps waiting on DRAM can be 100 times slower than one arranged to keep its data close.
And the expert's whole job is rearranging code to respect that hierarchy. They run a profiler, the tool that reads out the flood of low-level statistics the chip records while it runs. They spot a bottleneck, they fix it, and then the bottleneck moves somewhere else, and they do it again. It's a loop.
Right, and here's the observation that cracks the paper open. What makes those experts valuable is not that they can read numbers off a profiler. Anyone can read, occupancy is 6%. Occupancy, by the way, is just how much of the chip's parallel capacity is actually in use. 6% means the silicon is sitting nearly empty. The number is trivial to read. What's scarce is the diagnostic reasoning that turns that number into here's why and here's the fix. Heuristics people refine over years and bury in personal scripts.
So think of it like a blood panel. You hand a smart non-specialist a printout. 30 values, all technically right there in front of them. None of it tells them what to do. An experienced physician doesn't read the numbers one at a time. They instantly fuse this value plus that value into early kidney stress, do X. The diagnosis is the scarce thing, not the data.
And that's exactly where the existing LLM kernel systems made what the authors call a category error. They hand the model the raw telemetry and ask it to do two completely different jobs at once: interpret the hardware counters and write creative, optimized code in one shot. But reading counters is a structured, rule-governed task. Writing fast code is open-ended and creative. Jam them together, and the model gives inconsistent diagnoses and misses fixes.
So KernelPro's central bet is to peel those two jobs apart. Do the read the profiler like an expert step with deterministic tools that encode the heuristics, and only then let the model see the result. Instead of telling the model occupancy is 6%, a tool tells it occupancy is critically low at 6% because your shared memory usage caps you at 2 concurrent blocks. Switch to a warp level reduction, expected 3 to 5 times gain.
There are 15 of these things. They call them micro-profiling tools, and each one encodes a single expert heuristic as a rule with 3 parts: a trigger, an analysis, and a prescription with an expected improvement estimate. The output is never a number. It's a severity rating, a root cause, and a ranked list of fixes, sometimes with a code snippet attached.
My favorite is the stall tool because it's the clearest picture of what expert reasoning codified actually means. A stall is just a thread sitting idle, waiting on something. The tool reads 5 different counters for why a thread isn't issuing instructions, finds the dominant reason, and branches the fix to match. Waiting on memory? Cache it in shared memory. Use wider vectorized loads. Stuck at a synchronization barrier? Replace the barrier with warp-level primitives. Waiting on a branch to resolve? Replace the if statement with arithmetic. Same what kind of stall and why reasoning a human runs in their head, written down as a rule.
And there's a filtering step that makes this work, which I think is underrated. Before any tool fires, the system runs once and classifies the kernel. Is it compute-bound or memory-bound? Meaning, is it limited by raw math throughput or by how fast it can move data? That one question gates everything. A memory-bound kernel never gets bothered with tensor core advice. A compute-bound one skips the memory layout checks, so you get complete coverage of the actual bottleneck without diluting the signal with irrelevant noise.
Which connects straight back to your blood panel point, Juniper. The reason raw counters made the model worse isn't mystical. You dumped 200 numbers on it, most irrelevant to this kernel, and it pattern matched on the wrong ones. Chased a tensor core problem on a kernel that legitimately doesn't need tensor cores. Silence was better because silence at least didn't send it down a false trail. The fix is to pre-digest the panel into a diagnosis.
And one more design choice in that spirit. The tools fire proactively, not on request. In a normal agent setup, the model decides which tools to call, and it might call 3 and skip 10, missing the one that mattered. KernelPro instead fires every bottleneck-relevant tool, every iteration. It's the pilot's pre-flight checklist. You don't run the checks you feel like running. You run every check that could matter for this kind of flight, precisely to catch the thing you didn't expect.
Now, one profiler can't see everything, and this is where it gets concrete. KernelPro reads 3 of them, and the clean way to hold this is, what can each one see that the others can't? The first, NCU, sees inside the kernel, occupancy, stall reasons, throughput. The second, NSys, sees the system timeline, launch overhead, gaps where the GPU just sat idle between jobs. And the third is the clever one. It's called SASS, and it disassembles the actual compiled machine instructions, what the hardware was literally told to do.
Why do you need the literal instructions if you've already got the high-level metrics?
Because a metric can tell you that something's wrong, but not why. The classic case. NCU reports tensor core utilization, 0%. Tensor cores are the specialized units that do matrix multiply far faster than general math units. But only if you invoke exactly the right instructions. 0% could mean 3 totally different things. The kernel is element-wise and legitimately doesn't need them. Or it's using an older, slower instruction generation. Or, and this is the killer, it's silently falling back to scalar code while looking fine from the outside. The metric can't tell those apart. Reading the actual instructions can.
It's checking the receipt against the kitchen. The bill says the dish was served. Reading the SASS is walking into the kitchen to watch whether they actually cooked it or quietly plated something else.
And here's the payoff for that, from their production run later on. The SASS tool flagged 37 candidate kernels that compiled fine, ran fine, produced correct answers, and emitted 0 tensor core instructions. 37 silent scalar fallbacks. From the outside, indistinguishable from a real, slow but working kernel. No utilization metric on Earth could have caught those. Only reading the machine code could.
So that's the interpretation layer. But there's a second half to KernelPro, and it's the part that lets it keep going when things fail, which they do, constantly. The technical core is next, the search that wraps the whole system. It's the densest stretch, and it pays off in a single concrete fact, a task where the system failed 43 times in a row before it wrote one line that worked, and didn't give up.
The search is Monte Carlo Tree Search, MCTS, the algorithm famous from Go engines. The idea in one breath: you're facing a tree of possible move sequences far too big to explore fully, so you grow it selectively. You push effort down branches that have been paying off, but you keep some budget to probe neglected ones, because the richest vein might be down a passage that looked unpromising. Explore versus exploit, balanced.
Think of it as caving with a finite supply of rope and headlamp battery. You can't map every tunnel, so you go deeper down the passages that keep opening up, but you spend a little checking the gaps you've ignored.
And the reframe that forces all their custom machinery. In a normal LLM tree search, a node is a cheap reasoning step, a branch of tokens. Here, every single node is a complete kernel. To create one child, you generate code, compile it, run it, and profile it. Nodes are expensive, real artifacts. That changes everything about how you're allowed to grow the tree.
So how do they grow it without burning the whole budget? You can't afford to expand every option at every node.
Two adaptations carry most of the intuition. First, asymmetric branching. A node that's a working kernel, something you can optimize, is allowed more children than a node that's broken and needs repair. That encodes a real observation. The space of valid optimizations is wide, but the space of valid repairs is narrow. Found a good room? Explore it generously. Hit a collapse, give it a couple of digs, and move on. In fact, a broken node gets 3 repair attempts, and if all 3 fail, it's marked dead and abandoned.
And the second one is the reward, which is where there's a genuinely elegant move. When a kernel works, its score isn't its raw speedup, it's the logarithm of the speedup. And the reason is the part I'd repeat to a friend. 100 times speedup on garbage code that was trivially terrible to begin with would otherwise dominate the entire tree and drag the search toward easy junk. Taking the log compresses those giant easy wins.
It's grading effort, not raw distance. Getting an elite marathoner 2 minutes faster is a real achievement. Getting a couch potato to jog a mile is impressive, but it's a different category, and you shouldn't let it outrank the marathoner just because the raw number's bigger.
Exactly. A 2 times gain on already tight code is arguably harder than 50 times on a mess, and log scaling reflects that. But the reward does a second, sharper job too. A correct kernel with no improvement scores 0. Incorrect output scores -2. A crash scores -3. So a correct but mediocre kernel always beats an almost correct broken one. There's a hard wall at correctness. The search can never get seduced into polishing something that doesn't actually work.
And there's an append-only memory the system keeps across iterations, so it doesn't repeat dead approaches or lose a file path it already found. I'll flag. That one didn't really earn its keep, and we'll come back to it.
So where we are. Split interpreting the profiler from writing the code. Hand the interpreting to deterministic expert tools. Fire only the ones relevant to the actual bottleneck, and wrap the whole thing in a tree search that's patient through failure and refuses to be fooled by easy wins. That patience is concrete. On one task, the NetVlad kernel, the system failed 43 straight times before its first working version. Then, profiling guided refinement took it from below baseline to nearly 3 times faster in 2 steps. A fixed, single-shot approach would have quit at attempt 1.
So does the whole thing actually hold up? On KernelBench, that's the standard benchmark, 250 kernel tasks across 3 difficulty tiers, from single operations up to full model architectures. The prediction from all this is that comprehensive interpreted feedback should beat both raw data and silence. And it does. Remember the ablation ladder? Raw counters, 1.8. Nothing, 3.3. The full tool pipeline, 4 times. The tools alone add 125% over the no feedback version.
And the headline benchmark numbers? Geometric mean speedups of roughly 2.5, 4.5, and 5+ times across the 3 levels, with the prior best system sitting around 1.5, 2.5, and 1.5. The hardest tier, full architectures, is where the margin is widest. Every component was ablated independently with proper significance testing. Tools, the tree search, the proactive firing. And the tree search alone beats greedy by 26% on average, and on individual tasks by up to 10 times.
Before this sounds like a clean sweep, I want to put the real caveat on the table now, plainly, because a sharp viewer is already forming it. 2 things. 1. Every speedup here is measured against PyTorch-eager, the unoptimized default. Some of those reference implementations are trivially slow, which is how you get 100 times speedups in the first place. 5 times over eager PyTorch is a genuinely easier claim than 5 times over a competently optimized baseline. To their credit, they report cap tables and the gains survive, but it matters.
And the second?
The cross-system numbers aren't apples to apples, and the authors say so themselves in the appendix. Competing systems run on different GPUs with different optimization ceilings, report different kinds of averages, and test on different task subsets. One of them even trains on most of the benchmark and tests on the rest. So the advantage over prior work is real, but the precise multipliers, that 250% better on level 3 framing, those are not a fair head-to-head. I'd trust the internal ablations far more than the leaderboard comparisons, because the ablations vary one thing at a time on the same setup.
That's fair, and I think the strongest evidence isn't the benchmark anyway. It's the production case study. This is the payoff. There's a kernel inside a real training system called vOmni, a weight gradient kernel for a mixture of experts model that had been hand-tuned in Triton by expert engineers. KernelPro was pointed at it cold, told to write a kernel from scratch in raw CUDA.
And watch the trajectory, because this is the thing to actually look at, the climb.
The first attempt comes in at about 14 times slower than the expert baseline. A disaster. But each step, the profiler surfaces the specific bottleneck. The tools diagnose it. The code gets rewritten against that exact problem. And the curve climbs. 14 times slower, then roughly even, then just under the baseline, then past it. 18 iterations in, it lands at 1.23 times faster than the kernel the human experts wrote. And it found 16 other distinct correct kernels that also beat the baseline.
And the detail that makes this more than a number, the winning kernel contains 0 library calls. No QBLAs, no cutlass template. It's hand-composed from the lowest level primitives. This is the boldest claim in the paper. Most automated systems pick from a menu. They instantiate a high-level template, choosing tile sizes from preset options. KernelPro composed raw source from CUT building blocks, the way an expert does when no template fits.
And there's one decision in that run that I keep coming back to. At one point, the system reasoned that a particular fast memory transfer instruction would misread a neighboring expert's data under the model's irregular routing, and it deliberately chose an older, slower-looking technique instead, because the fast one would have been wrong. That's an architectural trade-off normally reserved for human kernel engineers. It didn't just stumble into working code. It reasoned about why the obvious fast path was a trap.
It's a strong existence proof. I want to be precise about what it proves, though, because this is where I land as the skeptic. It's one kernel on one GPU at 1.23 times. That's a modest margin, the kind where run-to-run variance and how hard the human tried both genuinely matter. It's an N of 1 production result. It absolutely demonstrates the system can match and edge past an expert on a real problem. That's not nothing. But beat the humans as a general claim rests on a single data point, and I'd want a dozen before I retired anyone.
That's a fair line, and I won't push past it. One kernel is one kernel. Though I'd say the existence proof is the hard part. Getting from can't beat experts ever to beat them once by reasoning like one is the qualitative jump. Closing from 1 to a dozen feels more like turning a crank.
Maybe. Crank turning is where a lot of methods quietly die, though.
Granted, there's a CUDA worth a minute, because it's a different idea entirely. Energy, not speed. The authors built an energy-aware version, and the question is whether you can make a kernel cheaper to run without making it faster.
And on a kernel called Swish, 2 versions came out at identical speed and identical memory traffic, but one drew about 12% less energy. Same arrival time, less power. The mechanism is the vivid part. The efficient version compiled to 56 instructions instead of 216. It chose a fast, approximate reciprocal over the IEEE accurate division.
And here's why that's free on time but not on power. The kernel is bandwidth bound. It's waiting on memory. So those extra 160 instructions execute inside time the chip was going to spend stalled anyway. No wall clock cost. But the silicon still burns power running them. It's 2 cars arriving at the same red light at the same moment, one with its engine needlessly revving the whole way there.
And to be honest, the way they want it, this is preliminary. 1 data point, 1 simple kernel. And the kicker? The win came from the rewards instruction count term, not from any of the 4 dedicated energy tools they built for exactly this. Those didn't even fire on the winning case. So, first energy-aware kernel agent is a real direction resting on a single demonstration. They say as much.
Same honesty showed up in the ablations, actually. That search memory you flagged earlier? Listed as a headline feature, it added 6% and didn't clear significance. They reframe it as helping early convergence rather than final quality, which is the honest read, but it's weaker than the billing.
Which I actually count in their favor. A paper that tells you which of its own ideas underperformed is a paper I trust more on the ideas that did.
So the big idea to walk away with. It's not the 4 times speed up, and it's not even the one kernel that beat the experts. It's the reframe underneath. When you connect a language model to a rich technical domain, the instinct is to give it maximal raw access and trust it to sort everything out. This paper is a measured, statistically defended argument that the instinct is backwards, that raw data without interpretation is noise that actively misleads, and the productive move is to build a deterministic layer that pre-digests the measurements into the kind of diagnosis a human expert would form. Diagnose first, then prescribe. And the authors point out it generalizes. Database tuning, compiler optimization, anything with measurable metrics, known failure signatures, and known fixes.
Which leaves a real question to chew on. KernelPro's whole edge comes from hand-encoding 15 expert heuristics as rigid rules, a checklist, not judgment. So where do you land? Is the future of AI in specialized domains exactly this? Models wrapped in carefully built interpretation layers that hand them expert-shaped diagnoses? Or is hard-coding human heuristics a crutch we'll look back on? And a big enough model should eventually learn to read the raw counters itself. If you've ever hand-tuned a kernel, you probably already lean one way. Say which and why.
The full annotated version of this episode is on paperdive.ai. Every technical term tapped to define, with links to the related papers grouped by theme, plus our weekly and monthly roundups.
Quick housekeeping. This script was written by Anthropic's Claude Opus 4.8. Juniper and I are both AI voices from 11 Labs, and the producer isn't affiliated with either company. The paper is Optimizing CUDA Like a Human, KernelPro out of Amazon, posted June 24th, 2026, and we recorded this 2 days later.
The trick was never giving the model a bigger pile of numbers. It was teaching it where to look. We'll see you in the next one.